Okay, great. Thank you for this introduction, and good morning to everyone. So I'm Mamour Sall. I'm a researcher at the CIMAP laboratory in Caen, in France. So my research topics are mainly about studying the effect of high energy ion irradiation in different type of materials. It might be optoelectronic materials like this one, so indium gallium nitride multi-atom wells, but also magnetic materials and nuclear materials. But today I will present our result on swift EV ion irradiation in these multi-atom wells, and with the aim for improving the efficiency of green light emission with light-emitting diodes. So this is maybe one of the most important slide, because this work is a collaboration between different groups across Europe, from Portugal, Spain, Germany, other labs in France, and it also involved many teams in my laboratory. So this is a slide for thanking all the people that were involved in this work, and of course I also thank all the funding agency, as you can see here. So this is the outline of my talk. I will first start with the context and motivation of the study. So this study is about nitride semiconductors, indium nitride, gallium nitride, aluminum nitride, boron nitride, and ceramides. These materials are well known. They have very nice properties, and they are used currently for application for detection and emission of light. They can also be used for high power and ultra high frequency devices. And we know that these materials can be subjected to ion irradiation. As a low energy ion, for example, for performing semiconductor doping and or p-doping, or high energy ion irradiation when they are used in harsh environment, like in the outer space. And because of this reason, I mean, the fact this material can be used in this kind of environment with high energy ion irradiation from cosmic rays, for example, we need to understand the effect of intense ionizing radiation in these materials. But today I would like to show that we can also use the intense ionizing radiation in order to improve the quality of this material. For example, the quality of light-emitting diode based that are made with these nitride semiconductors. So how to do this? This is a step image of a multi-quantum well, indium gallium nitride. So this is made of alternating layers of gallium nitride and indium gallium nitride. And this system is currently used for light-emitting diode in the blue region with very high efficiency of the LEDs. But the problem comes when we want to emit light in the green region, because the efficiency drops. And this is due to the fact that if we want to emit green light, we need to increase the indium content in the indium gallium nitride quantum well here. And by doing this, we create a polarization field across the quantum well, as illustrated here. And this polarization field will separate charge carrier. So this will decrease the recombination, and also this will also decrease the light emission. So we decrease the efficiency of the lens. And one way for minimizing this effect is by doing what we call quantum well intermixing. Typically, we go from a very sharp interface, like here, we have a very nice interface between gallium nitride and indium gallium nitride. And we go from this kind of interface to blurry one here. And by doing this, we can decrease the polarization field. So in this study, we propose to use ionizing radiation in order to do this kind of blurring interfaces. So maybe not everyone is familiar with ion irradiation. So before presenting the result in our material, I would like to have a few words about the ion matter interaction. So typically there are two ways of modifying materials with ion irradiation, two ways of creating defect. One way is what we call nuclear collisions. So these are collision between the projectile and the nuclei in the material. So we can have displacement of the atom because we have this collision between the projectile and the nuclei. And the other one is what we call electronic excitation. In this case, the projectile will transfer its energy to the electron. So in this case, the defect creation, the material modification will be an indirect process because the energy is transferred to the electron before going to the lattice. So this figure is an example of the evolution of these two parameters. So Sn is for nuclear collision, so direct collision between projectile and nuclei, and Se is the electron excitation. So these two parameters are represented for lead ion in aluminum nitride as a function of the ion energy. What we can see here is that at low energy, the dominant mechanism is nuclear collision, while at high energy, electron excitation become dominant. So as I said before, we would like to use ionizing radiation. This means we need to be in this range of energy loss, high energy loss, ionizing radiation, sorry. So for this, we will use what we call swift EV ion. So according to Ganil, swift EV ion are ion from carbon with energy above 0.4 MeV nucleon, but this is very subjective. But the point is, with swift EV ion, we should be in this region of energy loss with very high electron disturbing power. And as I said before, again, this in this energy loss range, sorry, defect creation is an indirect process because the energy of the ion, the projectile, is transferred to the electrons, and then it will be transferred to the lattice for creating defect. Typically, this is what will happen. Okay, we have an ion entering the material here. So around this trajectory, it will excite delta electrons. So this delta electron will create electron cascade, and then the energy from the electronic subsystem will be transferred to the lattice subsystem, to the atomic subsystem. So what happens generally is the energy transfer is high enough for melting the material locally. So here, for example, we have a melting part of the material, and this melted region is surrounded by very cold region, let's say at room temperature. So we will have a quenching of this melting part, and this will result in what we call ion track. Ion track is a modification of the structure of the material along the ion trajectory. And this is one of the characteristic defect we can have with swift EV ion radiation. Of course, this is not the only one, but this is the defect we look at more often, let's say. But we can also have less complex defect like point defect. So from this, I can maybe start presenting the result in our multi-quantum wells. But before presenting the result in indium gallium nitride quantum wells, I would like to show what happened in the binary compounds that make these multi-quantum wells. So the binary compounds are gallium nitride and indium nitride. These are TEM image of gallium nitride irradiated by swift EV ion. So on the left-hand side image, this is a cross-section TEM image where we can see the sample from each surface to deep in the volume. So each dark line you can see here are ion tracks. So each single ion will create this modification of the ion of the material structure. And these are the track I talked about before. In this image on the right-hand side, this is what we call plan view TEM image. So in this case, we observe a sample from each surface. So we can see the ion impact, each ion impact from the surface. And for this, in this example, you can see that the track is completely amorphous with a diameter of around 5 nanometer. So each ion will create in the material an amorphous cylinder. So from this, we could think that the gallium nitride is very sensitive to swift EV ion radiation, but this is not exactly the case, and I will try to explain why in the next slide here. So once again, how we create defect with electron excitation. The ion transfer its energy to the electrons. The electrons the delta electrons create electron cascade, and then the energy of the substance of the electrons are transferred to the lattice. So then we'll melt the material locally. This melting point will be, let's say, the initial point of track creation in the lattice. So from this, colleagues from Russia, Rivzanov and co-workers have used molecular dynamic simulation in order to follow the evolution of the melted region as function of time in two different materials. They did it in MgO, magnesium oxide, and also in aluminum oxide in sapphire. What we can see from this simulation is that 20 picosecond after the melting of the material in both materials, MgO and aluminum and sapphire, sorry. What we can see here is that in MgO, the remaining disorder is very low compared to the one in sapphire. This means that after the melting of the material, there will be a material dependent effect on track creation. In fact, in MGO, we have efficient crystallization of the melted region. This is not the case in sapphire. Why I'm talking about this is that gallium nitride, in fact, behave exactly like MGO. So this is again molecular dynamic simulation in gallium nitride. This was done by our colleague Miguel Segura from Lisbon and now in Germany. So we have here the melting track, the melting region in gallium nitride after the passage of the Swift heavy ion. So this is at 0.1 picosecond. When we wait after 100 picosecond, we can see that the track resulting from this melting is much smaller than the region that melt. So like in MGO, in gallium nitride, we also have this efficient crystallization of the track. So finally, oppositely to what we have seen before with track creation, amorphous track creation in gallium nitride, this material is in fact resistant to Swift heavy radiation. This is the first point. And the other one is when we look at gallium nitride irradiated at high ion dose. So this was done at this fluence of 5 × 10⁻13. In this case, we overlap the ion. I mean, all the ion, okay, one ion will create amorphous track. So as the track are amorphous, if we overlap all the surface of the material, if we irradiate the whole surface of the material, at the end the material should be amorphous because each individual track is amorphous. So if we overlap all the tracks, if overlap tracks on all over the material surface, we should be in amorphous material. But this is not the case. From this TM image and the diffraction pattern here, we can see that gallium nitride is still crystalline. At least the long range order is kept after irradiation. And this was again explained by using molecular dynamic simulation. For this, we went from one track created in the material. So this is a track created by one ion. And close to this track, we will make another ion passing here. So what happened is we create a second track here, which is amorphous. But at the same time, the pre-existing track is annealed by the second ion. So in fact, when we have overlapping of track, we create recrystallization due to the second track. So this is why gallium nitride is in fact very resistant to ionized radiation. First, we crystallize track by this process, but also when we overlap track, we have this recrystallization which is done by the second ion, let's say. So this was on the first binary compound, which is gallium nitride. So now I would like to show what happened in indium nitride. So this is again a STEM image of indium nitride irradiated by Swift heavy ion. So here you can see the tracks. All these lines are tracks of ion. And on the top of tracks here at the surface of the material, you can see these halox. So these halox are well known in many materials. This is due to explosion of matter towards the surface. In fact, if you remember what I showed before about track creation, inside the track, the material is hot because it's melted. It's under high pressure. And the surface here will offer a degree of freedom for releasing this pressure. That's why we have this exclusion of matter towards the surface and formation of this halox. And in indium nitride, this is very particular because the halox size is very big compared to other materials. Another thing we can see here is that the halox show dissociation of indium nitride. We have performed here stem hills chemical analysis of this part of the sample. So we have a halox here and the track below. What we can see here is that the halox is only made of indium. There is no nitrogen. So this means that indium nitride dissociates along the ion track. And of course, we have oxidation of the indium when the sample was put in air after irradiation. This is again visible here. So we have many tracks in indium nitride. On top of each track, we have this halox of different size. Once again, there is no nitrogen in the halox, but only indium, which is oxidized after putting the sample in air. So by the way, this is a way for creating indium oxide nanodots by using swift EVI irradiation. We can control the spatial separation of these nanodots. We can also control their size by playing on the swift EVI irradiation. But this is not the point I would like to point out here. What I want to show here is that indium nitride is in fact very sensitive to swift EVI irradiation compared to gallium nitride. So here still in indium nitride, we study the track in the volume of the material. So far, I just spoke about what happened at the surface with the halox. But here we can start seeing what happened in the volume. So when we look at the track in the volume, it's made of alternating region. We have this dark region here and light contrast region here. And this is the same, if we look at deeper in the sample, we will have the same structure. So we perform, again, chemical analysis using stem hills measurement. So first, we record the elemental profile measurement in position 1, so in the dark region, following this line, the blue line. And what we can see here is that in the track, there is a decrease of nitrogen content and an increase of oxygen. So we have, in region 1, we have nitrogen depletion of indium nitride, and the remaining indium is oxidized by air when we put the sample in air after irradiation. We did the same analysis in region 2, so in the light contrasted region here. So here we follow the red line. So what we can see here is that the nitrogen content is almost constant, and we have an increase of indium inside the track here. So region 2 is, let's say, indium-rich indium nitride region. So in the volume of indium nitride, we have this alternating region of nitrogen depleted region with oxidized indium, and also indium-rich indium nitride region. So to go further, we have also performed more hills analysis. Well, this time by looking at the nitrogen KH finite structure. So this finite structure of nitrogen is very sensitive to the local environment of nitrogen atoms. So first we compare the nitrogen KH finite structure in region 2. So region 2 is the one we have here. So this is region 2. In region 2, is the region where we have indium-rich indium nitride region. So we compare the fine structure in region 2 with the fine structure in a place where there is no irradiation. So fine structure in real indium nitride. So if you compare the two nice fine structure, we can see that the peak at the 403 electron volt, which is due to pi transition in these materials, disappear after irradiation in this region. So by irradiation, we destroy a little bit the structure of indium nitride in this region. Sorry. Okay, we did the same. So we record also the fine structure in region 1. And what we can see here is a new peak in the fine structure that appear at around 400 electron volt. And this peak is known as due to nitrogen molecules. So in fact, in region 1 here, we have nitrogen gas bubble that is created by irradiation. So this is to say that indium nitride is extremely sensitive to ion irradiation. So material dissociate. We have different region along the track, rich indium nitride region, a nitrogen depleted region with containing nitrogen bubble inside. So from this result with indium nitride, one could think that the indium gallium nitride with quantum well will be very sensitive to swift Higgs radiation. And this is not what we want, in fact, because we want to modify the material properties, but without dissociating the material like we have in indium gallium nitride. But when we look at the track structure in this multi-quantum well, indium gallium nitride, what we can see here is that, okay, it's not really clear when you look at, okay, this is a STEM HADF image. So in this case, okay, if you know a little bit about TM, we use very small camera lengths. This means we only collect electrons that are at high angle. So in this imaging mode is not sensitive to the strength field created by tracks. So what we observe, in fact, here, so this is a track. It's not really clear in this grayscale image, but it's more clear in this colorized one. So these two images are the same. This one is grayscale, this one is colorized one. In the colorized image, you can see we have a track here, and the track is bigger inside the gallium nitride layer than when we go near the indium gallium nitride. And once again, this imaging mode, HADF, is not sensitive to the contrast due to the strength field. So what we observe is really the real track, the modification done by the swift ion in the material. So this reduction of the track size might be due to the fact that the interface, like many interfaces in different material, act as defect sink. But the another possibility is that as we are in this kind of multi-quantum well, as you know, in multi-quantum well, we confine the carrier in the quantum well, so we will increase the conductivity of the material near the interface of the quantum well. So if we get back to the way track are created, so there is a melting. As we increase the conductivity at the interface, we will dissipate the heat. So this will result in a more resistant of the material at the interface here. So we have also performed using Hills analysis. This is atomic Hills mapping inside a track and outside a track. So outside the track, you can see here that the mapping is clear. You can see the atomic columns of all the elements. When we go inside the track, we can still see the atomic columns, but the map is a little bit blurry. But we cannot see a clustering of defect. This means that we don't have too much defect created by the swift ion in the quantum well. And this is, in fact, a good point. So from a point in the point of view of track creation, we know that multi-quantum well show strong resistance to swift EV ion irradiation. Now, what about the optical properties? Okay, what I did not say that is that the swift EV ion create track by the mechanism I showed at the beginning. So we have the ion exciting delta electrons and transfer of the energy to the lattice by melting. But this happens only if the energy transferred by the ion is higher than the energy required to melt the material. So by playing on the electronegative power, the value of SE here, we can be below the energy needed for the material to melt. So this means that there is a S threshold, electronegative power threshold for track creation. So for the following, we will use ion with electronegative power under the threshold for track creation. In fact, what we want is to modify the material by ionized radiation without creating the tracks, but because we know that the tracks are known as defects that can quench the luminescence of the multi-quantum well. So for the following here, all the irradiation was done, with swift ion without track. So these are photoluminescent spectra of the multi-quantum well irradiated by swift ion. So here with nickel and iron ion. What we can see here, okay, the black curve is the spectrum of the non-irradiated material. And after irradiation, what we can see here is that we lose the luminescence of the material. It's decreasing as we increase the irradiation dose for nickel ion. For iron ion, we completely lose the luminescence even at the lowest irradiation dose. And from previous experiment using excitation of photoluminescence, it was shown that this extinction of the photoluminescence in this multi-quantum well is in fact due to absorbing defect 2.8 electron volt in this material. And this absorbing band here is exactly the same as the one we found in gallium nitride irradiated by swift EV ion a few years ago. And we know that this band is in fact due to gallium vacancy. And gallium vacancies can be annealed at temperature as low as 400 degrees. So what we have done is to just annealed our multi-quantum layers after irradiation. So this was done at room. Okay, we irradiated the sample at room temperature. And after irradiation, we annealed the sample at the temperature at 450 degrees. What we can see here is that we can restore the luminescence in the green band luminescence, but at the same time we create a new band here, which this is a blue band in fact. And this can be understood very easily when we look at this figure. Okay, this shows the evolution of the band gap as a function of indium content in indium gallium nitride. So we go from indium gallium nitride content that emit light in the green range. So if we have a blue band here, this means that we have shift the indium content to the left hand side. Okay, we are somewhere here, let's say, and this means that we have created a mixing, because if we decrease the indium content, this means that we have created mixing somewhere at the interface. So by this swift EV ion irradiation and very low temperature annealing, we can create this quantum mixing we were looking for without losing the green luminescence. And this is really great result, because we can keep the green luminescence without we can keep the green luminescence. We can also see by the apparition of this blue band that we have created the quantum mixing that is needed for decreasing the polarization field that decrease the emission of the efficiency of emission of LEDs. So this brings me to the end of the presentation. We have seen that gallium nitride is very sensitive to swift ion radiation. This is not the case for indium nitride, which shows the material decomposition in ion plugs with a mix of indium-rich indium nitride region and indium oxide containing nitrogen gas bubble. We can also, by using swift ion radiation, create very nice indium oxide nanodots. We can control their density, we can control their size by playing on the ion energy. And what we have seen also is that the sensitivity of indium nitride to swift ion radiation is not transferred to the indium gallium nitride gallium nitride quantum wells because of the presence of the interface that act as defect sink. We reduce the sensitivity of this material, this system, to swift ion radiation. And finally, we have demonstrated that by using a combination of low temperature annealing and swift ion radiation, we can have efficient quantum well intermixing. And this is something we need for decreasing the polarization field at the interface. And we can also keep the luminescence in the green region. So that's all, and I thank you for your attention. If you have any question, I will be happy to answer.
Thank you very much, Mamour. Very interesting presentation. Do we have any questions from the audience? Please, if you have a question, type it in the chat, and then I will read it out to Mamour. I can ask a question until people may be typing. Can you or are you planning to apply this technique to other materials for emissions in different wavelengths? Is this also an option?
So far, no, but yeah, I would be happy to see if there is. Okay, so far I only work on nitride materials, but yes, this might apply to another system, of course. Yeah, if we need to just mix the interface, this might be a very nice way to do this.
We thank you very much, Mamour, and
Thank you.
Thank you everybody for joining.